In the previous live section, we did understand why we need the bounce logic at the input of the manual switch. This because if, in this case, here we have the FPGA, in this point we have a behavior like this. So when we close the switch, the FPGA see this bouncing at the input. Why? We can represent the analog threshold at the input of the FPGA. We can represent the analog signal when we close the switch as something like that. In this case, the input at the FPGA in this point will be something like this. Of course, these are the level at the input of the FPGA. So we need something to filter this behavior. In this case, we have a simulation with Model Sim, where when the input is less than an amount of clock cycle, we don't have any output pulse. When the input is greater than an amount of clock cycle, we have the output. So, to be more general, if Fc is the clock frequency of the FPGA, and we need to filter a pulse length of p-length second, we need to count Fc by pulse length clock cycle. For instance, if Fc is 50 MHz and we need to filter something less than 40 milliseconds, we need to count 2 million of clock cycle. In our circuits, we need to debounce the input manual switch at the input of the edge detector. Of course, we want to debounce the high level, so we need to put an inverter in front of the debouncer. The same logic is if we want to debounce a low level. So in this case, we design a circuit that have two flip-flops to avoid metastability on the input, and a counter that counts how many clock cycles we want to filter. This is an example of an entity that implements these circuits. We use a generic to define the debounce length, and then we have input clock and reset, input strobe, and output pulse, declaration of our internal signal, and then under reset, we reset all the internal state. On each rising edge of clock, we strobe the input in the two flip-flop. So we strobe on the first and the first on the second. Then, when the strobe is high, we start counting count +1 until the counter reach the debounce length. If the strobe goes low, the counter is reset. So, with this logic, we filter all the pulse less than the bounce length. When the counter reach the bounce length, we generate an output equal to 1. Let's see how to simulate the debounce logic. We have the debounce test bench that instantiate our debounce component and generate an input pulse using a process. Here there is in line 40 and 41 there is the generation of reset and clock. Note that I need to initialize the clock signal in order to make clock less than equal not clock after 5 nanoseconds. That generate a clock of 10 nanoseconds of period. So let's start and simulate. We need to set directory. You have to use lab 3. So create library and use the script to simulate. In this case, we have to compile and simulate. No view opt is used to tell the simulator to not optimize the test bench file, because if you optimize the test bench file, all the signals not used in the test bench are removed by the simulator and you can't simulate the test bench. So this no view opt constraint should be inserted in the test bench simulation. Then we recall a wave file that we saved in a previous simulation and start simulation. In order to change the input strobe, we use a counter, 8-bit counter that counts +1, and a selector that select a bit of this counter as input strobe. So we can see that if our input strobe is less than the bounce logic, so zooming in this case counter counts 1, 2 clock cycle, 1, strobe is 1, 1 and 2. Output pulse is 0. No output pulse is generated. When? Because our debounce logic filter all the strobe less than 15 clock cycle. In this case, the input strobe is 17 clock cycle. In fact, the bounce logic generates a pulse. To instantiate the bounce logic into top level, I mean, we need to put the bounce logic here. So open up the top level, and as you can see, we put the bounce component here, and connect this point as input and take a GPIO1D0 debounced as input of the OR. Here. As debug feature, we can use LED2 to see the debounced input. So let's lay out our design. Start Quartus 2 and generate new project. Set folder, create layout folder, and set the folder. Then the project is the top level. Add the files. And set the FPGA. Finished. At this point, we can close the project and set the pinout. So go to QSF. Okay. And add the pinout provided. Here. You can set also the pull-up resistor, copying the pull-up constraint from the previous project and pasting at the end. Save the QSF and reopen as a recent file. No, sorry. And reopen a recent project, the last project. Check in the assignment section if all the pins are okay. We can see the pull-up resistor on. Okay, and start simulation and start compilation. Okay. You can see technology map viewer, and you can see that we have all the module implemented into the FPGA as described here. We have the bounce logic, external button, or the edge detector, counter, and the driving of hexadecimal display. Now it's time to write your code. In the previous lab we we design the FPGA with edge detector, counter and segment driver. In this case, we need to add the bounce logic at the manual switch input. So, go in the lab3 folder, and in VHDL folder you will find 4 files: counter app, rising edge detector, Debounce VHD, and the top level DA0 FPGA. TB folder containing the simulation script. Open the file debounce.vhd and complete the code in order to design the debounce logic. Simulate the debouncer, setting as a simulation folder lab3/VHD and create work library. Simulate the code in order to obtain the behavior of the live section. Then instantiate the debouncer on the FPGA top level and set the bounce length to 40 milliseconds. Remember that the clock board is 50 MHz. Lay out the code, and if you need help, you can find the solution in the Lab 4. So let's program the FPGA with the bounced design. Turn on the board and start Quartus 2 Programmer. Start programming and wait for programming. Okay, the FPGA is programmed, so we can see that we can drive with a push button. Now try to use, as you can see, we have a blinking LED, 2 blinking LED, one that blink fast and blink with all the input glitch detected, and the second one that blink once. In fact, the counter counts +1 because we are filtering all the bouncing less than 40 milliseconds.